Okay, people, let's get started. This starts at beginning a series of lectures about how to solve the Nexus problems. This one's called Technology to Solve the Biodiversity, Food, and Water Problems. Technology is probably too strong a word. Maybe we should say like methods or ways or something like that. The technology necessary to solve these problems is already in hand. New technology will help, but it's not essential. Technology to solve the climate problem, as we'll see, I think it's the time after next, is actually now in hand. And the really interesting part about that, apparently we've got some sort of issues with the screen going, here it is, going blank. Technology to solve the climate problem is in hand. That's the message I'm going to be giving you now. What's really interesting about that is that that was not the message 1 year ago, the last time that the Nexus course was taught. It was still the case that the technology to solve the climate problem was much more, significantly more expensive than the energy system we have today. But all of a sudden now, in the space of 1 year, an energy system that doesn't emit CO2 at all is the same cost or a little less than the energy system we have today. Transition costs are still large. This is going to be annoying, but there's apparently nothing I can do about it. Okay, so let's go on. To solve the biodiversity problem requires solving the climate and food problems. So, let me see if, Raj, this thing is going off every 5 seconds.
Every 5 seconds.
Yeah.
Right, yeah.
Okay, I need some way to lecture. So,
yeah.
Is there
right, yeah. Okay.
Yeah.
It's the projector.
Yeah. Habitat loss to agriculture, as we know, is the single largest cause of extinction today. And with business as usual fossil emissions, climate change will become the greatest cause of extinction in the future. So you can't solve the biodiversity problem without solving the climate and food problems. That's what it means to solve the biodiversity problem in a very real sense, is to solve the climate problem and then also to solve the food problem without reducing habitat for biodiversity. You remember this slide? I did some calculations using the methods in the blue box that you won't be responsible for. The anthropogenic mass extinction under business as usual climate change alone is expected to knock out 33% of species by the calculations that have been done. You can't trust those calculations. Those are just numbers that somebody came up with some method. There's also the 60% of the biodiversity expected to be knocked out if you expanded agriculture into the remaining tropical forests, and that's because about 60% of the species are in those remaining tropical forests, and you'd lose just about all of them. That number's a little bit more solid. The solution is not to expand existing farmland, but we're going to need it all. And with that, the answer was that if you limit climate change to the extent that it won't cause a lot of extinction, and if you don't expand the agricultural system, that is, don't expand agricultural land, we end up with a loss of 11% of species. And 11% of species is hundreds of thousands of species, and that to a biologist like me just sounds horrible, all right? It's like, good God, that's a solution, 11% of the species. But there is there is a way to leave yourself with some hope on that. That estimate is based on species area curves. And species area curves, remember, are relationships between the number of species in a place and the area of the habitat for those species. And remember, it goes kind of as a power law, where area to the quarter power is the number of species. we're just going to have to, this is kind of like an interesting cognitive exercise. So good thing you guys have good memories because you can remember what was on the screen when it goes on. Okay? 11% of the species is hundreds of thousands of species, but those are based on species area curves. And those species area curves are the result of 10,000 years or more of relaxation of the number of species to the area that produces those curves. So for instance, if you have a bunch of different islands that are of different sizes, they have different species on them. The processes that put the number of species on those islands are processes that operated over thousands or tens of thousands or hundreds of thousands or in some cases millions of years. And so as far as we can tell, it takes a very long time for the number of species to relax back to a reduction in area. And we have natural analogs like this, right? So we know what happened when the sizes of islands decreased at the end of the last glaciation because sea level rise was so large at the end of the last glaciation. So islands like some of the Lesser Antilles and the Caribbean that are now a few square miles used to be thousands of square miles, as large as Cuba or Hispaniola, and we know how fast the species responded to them. So in the next 100 years or so, we might expect a few hundred extinctions of the 5,500 mammals and 10,000 bird species, rather than 10% of them, all right, which would be hundreds of mammal species and an order of 1,000 bird species. And so this gives us time, over the long term, this gives us a millennium to actually figure out what to do. And over a millennium, quite frankly, I think we as a species are either likely to be extinct, groveling around with a very different sort of existence, or be technologically extremely advanced and able to, for instance, produce our food on a much smaller amount of arable land. Right? At least that's possible. Now, I've shown you this before. This is an environmental Kuznets curve, and it is also relevant to this issue of giving yourself some time. So for a bunch of different environmental problems, as people become richer, you see GDP per capita on the horizontal axis. First, the environmental damage gets larger, and then people reach some sort of intermediate wealth at which environmental damage is maximal, and then it starts to decline again. And I've got a couple of plots here. This one shows the amount of deforestation in terms of GDP per capita. And although there's scatter all over the place, you see a decline, right? It's declining at the high end. So many societies are now what looks like past that part of the Kuznets curve. And what's interesting, for instance, most of Latin America now is net reforesting. That doesn't mean that we aren't still losing old growth habitat, but there's more forest each year in Latin America rather than less forest each year. It's not the same kind of forest, all right? There's ongoing destruction of primary forest, but the amount of secondary forest, abandoned agricultural land primarily, coming in exceeds the amount of primary forest going out. So it looks like Latin America as a continent is on the other side of this Kuznets curve. Other places still aren't. And I've got one other one to show you, and this is meat consumption. I find this fascinating because it shows finally a hint of a Kuznets phenomenon there. You see, the wealthiest societies have a little bit less meat eating. And yeah, it's, you know, you can squint at it and you think, yeah, that's probably statistically significant. But it's the ascending portion of the curve that people talk about all the time. Yeah. So this is a curve that shows that it's not just meat that has changed in the diet. The kind of meat has changed. And in particular, this is U.S. consumption. And you can see that beef has been going down since the mid-1970s. All right? U.S. meat consumption per person has gone down as chicken consumption has gone up. And of course, this is a good deal because beef is the worst thing for global warming. The worst kind of beef and other ruminants, but we don't eat a lot of lamb as a species. And so this is a histogram showing the kilograms of CO2 per kilogram of food. And the number is extremely large for beef, and it's much, much smaller for chicken. Remember this table we looked at before. The top is feed conversion, kilogram of feed per kilogram of live weight. You can see that chicken is 4 times more efficient than beef, and if we look at kilogram of feed per kilogram of edible portion of meat, it's more than 5 times more efficient. So 25 versus 4.5. So this change in the kind of meat consumption is also good news for the greenhouse problem, and actually also good news for the food system. You require less arable land to feed a chicken and produce a kilogram of chicken than you do to produce a kilogram of beef. And it's not by a little bit, it's like more than a factor of 5, okay? So, in addition, chicken requires 4 times less water than beef, mostly because of the evapotranspiration of the feed plants that go into raising those animals. All right, so the 2050 food demand, again, is caused by several things. First of all, the population, remember, grows from the current 7 and change to 9 to 10 billion by mid-century. GDP per capita, if the world is smiling, at least triples. Meat demand perhaps quadruples as people become more wealthy. Food demand doubles. And with all this doubling and tripling and quadrupling, nonetheless, almost every study, and I reviewed all of these things. I didn't know any of this stuff on food, or in particular on food or water, 2 years ago, and spent months and months and months reading the literature, so I'm relatively current on it. And I was amazed to find that just about every serious student of agriculture has concluded that existing technology can meet the mid-century food demand on the existing arable land if we do some relatively simple things. And that's really an astonishing claim, because if you read the newspapers, you would conclude the opposite. There are a couple of extreme proposals, a couple of extreme analyses that suggest the opposite. But if you look at them carefully, they make extreme assumptions that aren't consistent with historical trends. So they'll have to say, well, the historical trend in yield improvements is going to stop, right? They'll make a claim like that, right? But virtually every analysis, including by people who aren't predisposed to sort of like the agricultural system. And a good example is John Foley, and I actually have that on the reading list, right? So you should read this paper. It's easy to read, and it's one of the most heavily cited analyses. John is currently president of the California Academy of Sciences, and if you're in Golden Gate Park sometime and you're in the room, call him up and tell him you read his paper. Like that. All right, so Foley has a series of solutions in this paper that are worth going through. And what's at stake here is to try to double the food production on the existing land by mid-century. And the first thing Foley says is that a 58% increase in production can be achieved by simply closing 95% of the existing yield gaps. Now, what are these existing yield gaps? These are the new calories in that map up top from closing yield gaps for staple crops. And you can see there are all kinds of places in the world where it's red. And that means that doing what we know how to do, we could get more yield of staple crops out of an existing hectare of land or acre of land than we can get now, and a lot more, okay? New calories, these are millions of calories per hectare. And you can see that a lot of this is in India and China and places in sub-Saharan Africa like you might expect, but a lot of it's in Eastern Europe. And there are even some places in the United States where we could, with existing technology, do a lot better. There's a bunch of different reasons for this. So take the case of corn, for instance. This is the percent of potential yield obtained. And you can see that Midwestern corn and European corn is green, meaning almost all of the yield attainment that can be attained for corn is currently being attained. But there are other parts of the world, notice Mexico and sub-Saharan Africa and much of India and China, in which less than half of the potential yield of corn per unit area is actually currently being attained. And so what's the reason for this? And there are a bunch of reasons. In the case of maize, the red is nutrient limitation, purple is nutrient plus water, blue is water, and green is that the yield ceiling has already been attained. And you can see there that by and large, the places that haven't attained the possible yields, the maize is nutrient limited. Look at sub-Saharan Africa, look at Eastern Europe, look at Mexico, look at India, look at even parts of China. And so the problem there is that fertilizers aren't being applied to the land. Now there are of course negative consequences of fertilizer use, including runoff and dead zones. And so there's a need to apply fertilizer in a more environmentally sensitive way, but we know how to do that. This is fertilizer application in 2010. And you can see that the pink and the kind of reddish colors are the big ones. And the scale, when it comes back up again, Jesus is enough. The scale is logarithmic. So it doubles. So 3 to 5, 5 to 10, 10 to 20, 20 to 40, 40 to 70. So red is 220 kilograms per hectare. That's an awful lot of fertilizer. And the places that are sort of are China and India, the northern Midwest. So a lot of India, especially along the Gangetic, there's really heavy fertilizer application. But there are other places, most of sub-Saharan Africa, for instance, where fertilizer application is extraordinarily light. That's 1 to 3 kilograms per hectare. Whereas in the northern Midwest, it's 20 to 200. The efficiency of irrigation is also critical. Irrigation is used for 34% of crop production. We'll talk about this later in the lecture, but I wanted to point it out here because although water isn't a nutrient, it kind of operates as a nutrient. You need water to grow plants. It's like a factor that you need to add to some land to produce it. And irrigation efficiency varies by quite a bit. This is the percent of water lost via transpiration as a function of in the numerator and the amount of water added through irrigation in the denominator. And the red colors and the orange colors say that most of the water is lost due to evaporation and actually doesn't make it into a plant, meaning that the irrigation system is extremely inefficient. And if you look where that is, it's really the Indian subcontinent that leaps out at you. The whole Indian subcontinent is water limited, and yet they're not applying irrigation in a way that actually makes it to the plants. So there's some room to be made up with irrigation as well as with nutrients. This shows that in a very graphic way. This is the liters of water that you have to add on irrigated land per kilocalorie of food that the land produces. And in the entire world, you can see it's not very pink, except for India, where the amount of water that you're adding per kilocalorie worldwide stands out as a universal world anomaly. All right. So this just means that there's extremely still inefficient irrigation in portions of India. So the story for much of the world, particularly sub-Saharan Africa, is fertilizer use. But the story in India is inefficient irrigation. This is just one other graph from a report by this guy named David Mould. If you're interested in this sort of thing, it's the one to read. When it comes back up, it'll actually, there it is. So this is yield in kilograms per hectare, and this is water productivity, which is in per unit of evapotranspiration. This is kilograms of food produced per unit of evapotranspiration versus yield. And you can see that the efficiency that you're getting of food per unit of water added is very low at the low end of this curve, and that corresponds with yields that are very low. Now, what does this tell you? It says that the inefficient agriculture is happening in places that have poor yields, and these are primarily impoverished farmers. All right, so this is all related. These things are, all related. And these are different staple crops, not just maize, but wheat and rice. There's a regression curve there. So the first solution is to close existing yield gaps, and we already know how to do that. And we just, because of poverty and other problems, haven't done so. All right. It's primarily a fertilizer story. It's particularly in sub-Saharan Africa, but it's also an efficiency of irrigation story, particularly in India. The second problem is one that, unlike adding extra fertilizers, has no negative environmental externalities that I can think of. And this is to reduce food waste. A third to a half of food produced by our species is never consumed by people. It's actually just wasted. It spoils on the way to market. It spoils in the field. It spoils in your refrigerator before you eat it, or it's left on your plate because you didn't want to eat the whole thing. And so in developing countries, 40% of the food is lost because of storage and transport problems. Developed countries are better at storage and transport, but people put too much on their plates and then throw it away. All right. So if you're wealthy, it's because you're careless, and if you're poor, it's because storage and transport are inefficient. And so you can get sort of 14% of the doubling you need just by reducing food waste. This is at least Foley's analysis in ways that would actually save money. And the third part of Foley's solution is that 28% of the increase we need can be done by shifting diets. And he and his many colleagues, I shouldn't just say he, there's like, I don't know, 50 authors on that paper, a lot of people. But he doesn't propose in any way, shape, or form that people give up meat in their diets. And it's not because he doesn't believe they should, it's because he doesn't believe they will, okay? There's a very strong relationship, as we've seen, between meat consumption and diet that maybe has a bit of a Kuznets curve in it, but still has this massively ascending arm as people become wealthy. And so the question is, could we achieve mild shifts in diet of the kind that we've seen in the United States to reduce the amount of food that is going to animal feed and increase the amount of cropland that is actually feeding people directly. And so he thinks that this is relatively simple to do, that 16 crops going to 100% human food is enough to do it. He has a very detailed plan. He and his colleagues have a very detailed plan for how this would work. And if you read it, it passes the lab test. It's in the supplementary material for that paper. You're not responsible for it, but it's worth reading. Now, none of this talks about the primary issues that Americans talk about when they talk about our food system. None of it's talked about organic farming. None of it's talked about slow food. None of it's talking about local food production. The problem with corn in the American diet, with sugar, with obesity, with diabetes, with insecticides, with herbicides, with dead zones off the coast, with genetically modified crops, and with biofuels competing for arable land. I haven't talked about any of those things here. And I will talk about those in the next lecture. But the issues that preoccupy people in developing countries, which are these issues, are not the issues that preoccupy the world or that that dominate the problem of supplying enough food to the planet by mid-century. In about 1 billion seconds, we're going to have to double the amount of food we supply to the planet. And these issues, however important, are of a different kind than producing enough food to actually feed people so that they don't starve. Right? We'll talk about that next time. So I want to turn a bit to the water problem. Solving the biodiversity and food problems requires solving the water problem because of this issue of inefficient irrigation that I talked about when we talked about the food problem. Because if you don't solve the irrigation problem, then you have to expand arable land. And if you expand arable land, then you cut into the land for the remaining biodiversity and you cause a mass extinction, right? So they're all tied together in this way. Even though the water problem is a minority component of the food problem. You remember this diagram where there's a little tiny dot you can't even see when it's on of the amount of fresh water that's actually available, whereas the big blob is the total amount in or above, on or above the earth. It's the oceanic water. It's still a tiny amount of water relative to land in the world. This report, Water for Food, Water for Life, is the best one I found. It's pretty old right now. It's a 2007 report, but if you're looking for a sort of authoritative guide on the water problem, this is the best one I came across. And I read a lot of them, including some that are much more prominent. Peter Gleich is the person who everyone knows as the sort of grand poobah of the water problem. But I'm recommending this one if you want to look at one thing out there. You're not required to, obviously, for the course, but for anybody who's particularly interested in this. Now, what is the water problem again? At least in this context. 50 years ago, water withdrawals, that is, the water that we pulled out of the hydrologic system, particularly rivers, are a third of what they are today. So that water that we're pulling out of rivers that we could be using for irrigation 50 years ago were 1/3. They gone up by a factor of 3. That's a lot. So now many rivers are insufficient to supply the water that we're withdrawing. And so a bunch of rivers that used to make it to the sea no longer do. The most spectacular example is the Colorado River in the south and west of the United States, which no longer makes it to the sea because the water is all pulled out for irrigation. There's an attempt, incidentally, in case I forget to say this, to organize landowners, to organize a bunch of really wealthy people in the West Coast to buy up enough water rights to reestablish the Colorado River. And the Environmental Defense Fund 2 years ago organized a group of landowners to spontaneously and voluntarily withdraw their withdrawals from the water market and reestablished the flow for a little while of the historical Colorado River for the first time in decades. And the interesting thing was that all of a sudden the local community in Mexico saw the river coming down, and so they organized this festival spontaneously. It happened, it made the news. It was really sort of a marvelous human thing that happened. And it's a shame, as we'll see in a minute, because the withdrawals from the Colorado River are not rational. They aren't economic. They aren't even beneficial in many ways to the landowners. People do it because of the nature of historic water rights. And so this is one river I hope we can restore. It doesn't have to be restored to historic levels of flow, because the historic levels of flow were dominated by spring runoff in the Rockies, when massive amounts of water would stream down the river. And most of the year the flow was much less. So by restoring the flow to the historical average flow, you still can withdraw most of the water for irrigation, but yet maintain the ecosystems along the river and the value of it for the communities that line it. Okay, so with today's water use efficiencies, withdrawals from rivers, if you just look at the irrigated water demand, are going to have to increase by about 80% by 2050. So they already have gone up by a factor of 3, and they'd have to double like again, right? And so this would be bad. But the food plans that Foley and others talk about believe that 75% of the country's increased food demand can be met on rain-fed lands, not on irrigated lands. So most of the doubling of the food, 3/4 of it, can be done by improving production on rain-fed lands and not adding irrigated land. 3/4 of the remaining quarter can be met by increasing the water productivity on the lands where the water productivity of the irrigation is very low. Most of the irrigated water is being wasted by going into the atmosphere without making it through a plant. And remember, South Asia was the dominant target there. And so this leaves only 1/4 of 1/4 necessary for increased irrigation. So 1/16 of the total problem, all right? So although this sounds daunting, that we're going to have twice as much water in the year, that we need twice as much if we did it the way we do today, we won't have to, in fact, do that. This is Molden's, a graphical analysis from Molden's work. It shows today the blue is evapotranspiration by irrigation. It's the amount of water that goes out of plants today because of irrigation. Green is the evapotranspiration by rainfall. And so you can see that most of our food system today, the evapotranspiration is actually rain-fed, that's the green portion, and a small fraction actually comes out from irrigated water. Now, without productivity improvements, the total is going to have to grow according to the brown bar in Molden's analysis, and that's a big jump, right? The big increase in the total amount of water withdrawals. But Molden has a bunch of different policy scenarios that would lead to a reduction in the brown and to no large increase in the blue. So, for instance, this comprehensive scenario is the one that he proposed. He's got this rain-fed scenario, an irrigation scenario, a trade scenario, and a comprehensive scenario. A guy like Molden, when he says comprehensive, it's the one that he believes in. Right? Comprehensive is, you don't choose that word lightly, right? You know, comprehensive means everything I know. And what Molden says here is that irrigated evapotranspiration goes up a little bit, but almost all of that is caused by increased efficiency. The amount of rain-fed goes up a little bit, but thus most of the doubling in food demand is actually handled by increased productivity on the existing lands. All right, see that? This is a harvested area. It's the same sort of graph. But since this is, are you guys ready? Yeah. Can you get that up onto this? Yeah. Tell me when you're ready, because I'm not going to switch. I'm going to keep lecturing until you are.
Yes, sir.
Thank you. All right, so this graph shows the region, sub-Saharan Africa, through the OECD countries. I think it just came up. Oh, there it is. This is scope for improved productivity in irrigation. You can see that there are two highs here. The highs are South Asia and East Asia. That's what we saw before. Irrigated areas, that's the region of the world where it's lagging. Where if you look for scope for expanded irrigation, you see that there's one high here, and that's sub-Saharan Africa. It's actually possible to increase irrigated agriculture in sub-Saharan Africa. Let's do it. Okay, now I'm just gonna, you're gonna have to, oh, here we go. Now this is a bush fix, right? All right. All right, it's an alternative geometry. It's great. I love it. All right, we're good to go, guys. Thank you very much.
Thank you.
And obviously, we're going to get the main item fixed.
Right.
Yeah, I like it.
I mean,
No, don't worry about this. Just leave it. Just leave it. I can make it till the end here easily. I don't know. It's like I think there's probably a place where if you stand, yeah, right there. That's perfect. So if you'll all just come up here. All right, maybe not. Okay. All right. So what's the story with irrigation technology? What are irrigation technologies? You know, and they're really not very exciting. There's surface flood irrigation where you like bring water in and then you like open the ditch and the stuff flows onto the land. And that worldwide is about 60% efficient if you do it right. Doing it right means lining the canals with a substance like clay so that the water doesn't seep into the soil along the canals. All right, so there's like simple things that can be done and that are done in places where they've invested a little bit in the system. Sprinklers are more efficient, so that goes from 60 to 75% efficient. Sprinklers are like those big things that you see in the American West that are going around, you know, on the wheels, making the crop circles, you know. And finally, there's drip irrigation that's done almost no place. The right-hand little pie diagram shows blue is the flood irrigation in the world, 95% of it. And drip irrigation is this tiny little fraction of 4%. As far as I know, this worldwide center for drip irrigation is in the Negev. All right, the Israelis are really good at it, and that's putting individual drops at the base of each plant by putting a little perforated hose that runs around the thing and actually delivers individual water to drip irrigation is 90% effective. Even in a highly evaporative region like the Negev. And so that means that there's a 4x decrease in the amount of water wasted if you just change the irrigation technologies. Now, desalination is something people always ask about, and that's why I put this on here. I actually looked into it when I was, yeah.
I was going to ask, what percent of the world uses sprinkler?
Yeah, so I actually, it isn't on that stupid diagram. I just realized that while I was talking to you. I'll look it up for you, but you know. I don't know what fraction of the world uses sprinklers. I actually have no idea. And it's probably in my notes somewhere, but right now I have no idea. Okay. So desal, people always ask about desalination. Desal has become much less expensive than it used to be, but it's still really expensive. Nobody even talks about it. Nobody even proposed doing desalination to irrigate crops. I looked it up, and it costs $14,000 for a hectare to put a meter of water, which is kind of what you need for a crop on the land. That's a giant amount of money. Crops don't yield $14,000 per hectare. So it's just super expensive even today, and it's going to remain so. I like Moshe Dayan's quote. I don't know if you know who Moshe Dayan was, but he's a famous Israeli general. And at the time, there was a lot of discussion about whether or not Israel was going to war with Jordan and Syria over the Jordan River, right, the dominant source of irrigated water in several of those countries. And he says, why go to the price? Why go for the price of 1 week's worth of fighting? You can build 5 desalination plants. So he says you'll never go to war over water, and yet no one ever does desal for it. So although he said that, I actually think it's wrong. Okay, that's my first opinion. Okay, there's also crop breeding and genetic engineering. So we're constantly improving the water use efficiency of individual crops, and there's a lot of room that can be done on that. But the big technology that's needed is just to implement more efficient irrigation technologies, and we know how to do it. I want to close today with an example that shows that most of the impediments for improving the use of irrigated water in the world are now not technological, but are in fact political. And one of the best examples is from the United States. This is the Colorado River Basin. And the Colorado River Basin is a freaking disaster, all right? So that's the flow in the Colorado River. And the bottom there is the delta where it's supposed to go to the sea. March 22, 2014 is when that EDF effort reestablished the flow, right? You can see the river making it to the sea again. But it basically doesn't make it to the sea. The last time it made it naturally was in the late 1990s, and for over 20 years, there's been no natural flow to the ocean. And the question is, why not? What happened? I'll get to that in a minute. A second example of the Colorado River being a problem is that most of the water for metropolitan Las Vegas, and much of it for metropolitan LA, comes from the Colorado River. And it's stored in this giant reservoir called Lake Mead. Who's been to Lake Mead? Anybody? A couple of people have been to Lake Mead, not too many. The water level, because of withdrawals in Lake Mead, have been continually going down. You can see the historic water level in the upper left-hand corner and where it is now. And this has actually had really serious consequences for LA. You can see in the lower left-hand side, there used to be two intakes for the water system that supplied LA and Las Vegas. And the water level dropped past the first intake and was just about to drop below the second intake and cut off two of our major metropolitan cities from their fresh water, all right? And so at the expense of several $100 million, they put in this third lower intake in 2016 finally to keep the thing going. But Lake Mead just continues to lose water. And why are we mining it down? And the answer is that there are historical water rights that were established at the end of the 19th century, where each landowner has, as part of the deal of owning the land, has a particular amount of water they're able to withdraw from the Colorado River and put on their land. And if they don't do that, they actually lose the water right. So it's a perverse incentive to use water that you don't even need. Now, alfalfa, the upper left-hand graph shows, is the highest water-using crop in the United States. Alfalfa uses, than any of the other major crops, alfalfa uses more water per unit land area than any other crop. And there's a graph there of where alfalfa is grown, and the red circle shows that there is a dominant alfalfa growing region in the desert in the American Southwest. So we're growing the most water consumptive plant, which is a beef feed, in land where all of the water has to be irrigated water. And that's because these landowners are trying to dump the water that they've been given in their water rights so that they don't lose them, okay? It's a perverse incentive written all over it. It's actually interesting how those water rights came to be, particularly in this region. There was an event in the 19th century where the attempts to modify the course of the Colorado River went haywire, and the river jumped its banks and formed this thing called the Salton Sea, which has been declining ever since. And so the government of the United States said, well, who can solve this thing? The Colorado River is running in the wrong place. We've made this terrible error. How do we reestablish it? They looked at their assets, and the only entity that had this sort of infrastructure and equipment to restore the position of the river was a big railroad company. And so the railroad company says, okay, I'll do it, but we're going to own the water, all right? And so And so they gave the water rights to this railroad company that subsequently sold off the land and the water rights, and that was the origin of it. So most places that are in the developed world with low irrigation efficiency have either no regulation in the developing world, or in the developed world, historic water rights, exactly of the kind I've shown. A non-transferable right to a landowner to withdraw a set amount of water. You can't give it to somebody else. You can't sell your water to somebody else, nothing like that. Now, what's now known is that if instead you give each landowner a water entitlement to a set fraction of the stream or groundwater, and this is the critical part, the ability to sell unused water. If you can sell your unused water to somebody else, then all of a sudden it gives the individual landowner an incentive to use the least amount of his or her water so that they can sell the most amount of his or her water and make extra money. So each year, the water allocation has to be set by some financially disinterested body, so the total withdrawals from the river remain at sensible levels. But underneath that cap, they can be distributed in the way that the previous bullet described. So this was used successfully in several locations now, most notably in Australia, where 30% of water is now traded in this way. And it just solves the problem, because then each individual landowner has an incentive to maximize his or her water use efficiency rather than minimize it. There's a real attempt to do this in California, but there are, of course, political headwinds for doing so. And it's an extremely interesting area of policy, I find, because it's like Bob Cohane said yesterday, it's all about the incentives. So how do you incentivize landowners to give up historical water rights? All right. Well, the ability to sell them is a pretty big part of it. All right. It's a big part of it, because if you can sell your water rights, you have an extra source of income. But if we are to solve water problems in the West, and even places without water rights, for instance, groundwater is usually not governed by water rights. You can just drill a hole and start pumping. You're not worried about whose water you're taking it from, in the same aquifer. Instead of withdrawing water rights, we're probably going to have to increase them to get that to work. So if we gave collective ownership of an aquifer to the people who own the land drawing from the aquifer, and did it with a system of tradable allocations, right, where you could sell your unused water, you'd actually decrease water use rather than continue to increase it. So why isn't this done everywhere? It's intended to, so just click, okay? And sorry about the technology. This won't happen again, but occasionally things fall apart. So that's the, those are, oh yeah. Yeah, there we go. Thanks, guys. And I'll see you again next week.